Well, hello everyone, and welcome back to Adrian's Digital Basement. I'd like to wish everyone watching a Happy New Year. And while I was thinking about all the things I did in 2025 and the things I want to do in 2026, I realized that one of the things I used to do a lot of, and I haven't really done in a long time, is work on a broken Commodore 64. This Commodore 64 was given to me by local viewer and friend of the channel, Paul, and Paul said that this thing wasn't working. It's in kind of rough shape, but specifically, I think it has a black screen and has some other issues that keep it from even running the DesTest cartridge. So I was thinking, let's kick off 2026 by trying to do something that I used to do a lot of, repair these 64s, and it has me kind of worried. Have I lost my ability to fix these things? Maybe, because I just haven't done it in so long. And perhaps I won't be able to fix this, or it'll really throw me for a loop and cause me all sorts of issues. So let's kick off this new year with a 64 repair. And without further ado, let's get right to it. So as I always start out with all of my videos, I have the ZIF64 hooked up to the bench, and this thing is totally working. I mean, it's amazing in a way that this computer still does work because it's running with these really cheap clone ZIF sockets, which are notorious for being unreliable. And in fact, the socket that's under this 6526 over here has some glitchy issues, and occasionally I'll get some random keyboard pushes. In fact, let's pop out the Easy Flash cartridge, and perhaps we can get it to misbehave. So sometimes, I mean, it's just not doing it now. So yeah, sometimes for some reason, I'll power up the machine, I'll just get a whole bunch of random keyboard pushes. And if I just open and close this ZIF socket, it just starts to work again. Now, if you can believe it, in preparation for this video, for trying to look at this broken 64, I actually went through all the other 64s I have at hand. So not including the ZIF 64s, I went and grabbed 4 bread bins and 3 64Cs to test them all to see if any of those were also broken, to maybe turn this into something like a little mini repair-a-thon. Well, and if you can believe it, every single 64 I grabbed and put down on the bench was working perfectly. 0 issues, and those are all machines, including the ZIF 64, that I have fixed previously, and they just continue to work. So even though 64s are known to be kind of unreliable, especially the bread bin variety, it just doesn't seem to be the case, at least for the stuff that I've worked on. Like whatever chips have gone bad on them, just I fixed them and replaced them or whatever, and then that was that. The thing just worked. I think even originally the ZIF 64's problem was it had a bad RAM chip or two, because it has one RAM chip in a socket besides the ZIF socket. So that was probably its original problem that kept this machine from working. Now, the reason why the ZIF 64 was on the bench, I just wanted to validate that the capture setup is working. I always stress the importance of that, because you don't want to go chasing your tail trying to fix a machine that doesn't seem to be working, when the reality is your power supply or your capture setup or your monitor, whatever you're hooked up to, your cables, things like that, are not working. Now, if you don't have an extra 64 to plug into, well, that sort of poses an extra problem. But I suppose what you can do is just really try to validate that your cables and everything else are good before you go trying to chase down a faulty machine like this one. Now, as I mentioned in the intro, this computer comes from Paul, and it says DesTest something purple border something something something. The machine's in pretty rough shape. Obviously, we have 3 missing keys with broken stems. Luckily, I have plenty of 64 keys and stems, so that's an easy fix. Judging by the fact that there's sort of this rubbery foam along the top edge of the computer, I presume this originally had an adhesive strip which held one of those keyboard covers. So it was a tinted plastic cover that covered your keyboard to keep the dust off of it. And I can believe that, because the keyboard's actually pretty clean considering the state of the rest of the machine, which is really grimy. And you would flip that cover up to use the computer and just close it when you were done, as opposed to using one of those vinyl covers that a lot of people use that just would keep the dust off of their computer. In a way, if that cover had been kept on this machine, then these keys would have never broken off. So that's kind of unfortunate. Let's see, are there even screws? Oh, there are no screws in this thing. Back of the machine, pretty typical. A little bit of that foam over here too, for whatever reason. I don't really get why. It says made in USA, so that's kind of cool. And the motherboard is definitely in the case. And the one odd thing is on the side, it says Mic 466. What does that mean? Who knows? With a top-down look at this machine, you can just see the broken keys and the general state of this machine. Let's take a look on the inside. I think what I might do for this troubleshooting exercise is I'm going to treat this as if I had never worked on a 64 before and this is my first machine. Well, at least from the basic troubleshooting steps that I'm going to do. And if you just got one of these for Christmas and it's a 40-year-old computer and it's not working and you didn't get one of those new Ultimate 64s, whatever, the FPGA based one that has just come out, well, let's go through all the troubleshooting steps that you might need to try to fix your 64. And to do all the work I'm going to do in this video, you can actually get by with using a Zoe ZT703 oscilloscope / multimeter. This is a scope and multimeter all in one. There are plenty of these on the market. You don't have to use this particular one. It's just the one that I have. And I don't know, I generally like this thing. All right, so first thing we want to do is want to validate the symptoms that were reported for this machine. So I'll plug it in the power supply, one that I happen to know works, but we'll check to make sure the voltages are good in a second. And this is my little adapter cable that has video out. It's actually from a VIC-20, or, well, I mean, so it's a VIC-20 on it. It's one that works with the VIC-20, because specifically this is just a 5-pin DIN connector. And the 64s, these later ones, especially like this, actually have more pins. If we flip this up, you'll see that there are more pins in there. Those extra pins are for the Luma Chroma or S-Video-like output. But the reality is, if you just want to test composite video, something like for a VIC-20 cable like this is all you really need. And it's the lowest common denominator, which is why, I don't know, I usually test with this. Certain old 64s do only have a 5-pin connector, just like the VIC-20. So this is the only cable that does work with those versus these later ones that have the extra pins. So for capturing composite video, I use something called a RetroTink 4X Pro. There are plenty of these types of devices out there. You can have very inexpensive ones or ones that are a little bit more like this, or I think there's a new 5 HD Pro 4K, whatever. It costs like $500. You can use any of those to capture this, or you can just use an old CRT monitor as well. Although, like I said, I always recommend testing, say, an old monitor first with something like a VCR or a DVD player, just to make sure that composite video input and audio input is working properly, so you don't go chasing down issues with a 64 that don't exist because there's something wrong with your actual display device. So if we turn on the computer, well, black screen. Now, one thing that we're not seeing on this particular screen, just the way my OBS capture is, if I switch the input to this, which is a full screen input, so it's the full widescreen input of the HDMI output of the RetroTink, when I turn on the machine, we do see that there is a single white pixel on the left side. That is totally normal for a 64. Pretty much all of the VIC-2 video chips produce that white line on the left side. Now on a CRT, you might not see that because it'll be off the edge of the screen, but when using a capture device like this, it typically will show you the entire NTSC video image, and that white line is normal. So it's actually a really good sign that we see that white line. We know we're pretty much getting a good video signal out of the 64 because, again, when I switch to this input, we're seeing a stable black image with a white line on the left side. It's not rolling, it's not flickering. That white line is perfectly vertical up and down. It's essentially what this machine does for a few seconds when you turn it on, as it does a quick RAM check. That 64 always starts with a black screen with the white line, does a RAM check, and then it will display the blue background with the text on top of it, as you would normally see when you enter BASIC. So right away, we can tell by the video signal that we see with that white line that quite a bit of this machine is working. The VIC-2 chip is what generates the video signal, and this small IC, the 8701, is used on later 64s to take the clock output and convert that into a signal, a timing signal that goes into the VIC chip. The VIC-2, which is the graphics chip again, takes the clock signal and then it actually divides it down and generates other clock signals used for the rest of the machine, including the CPU clock. Now, if I grab the ZIF64, I will show there's a totally different revision of 64 motherboard, and that's an older one that's in here. So it doesn't have that 8701 chip. It still has a crystal and an oscillator circuit, but then it uses this TTL logic to generate those same timing signals that one IC replaces. So Commodore was just trying to simplify things a little bit, so they went to that single little IC and just a crystal. And on the older machine, you always have more parts required for this timing circuit. Now, what would happen on a 64 if you had no clock input to the 64? Say the crystal was bad, very unlikely, but it could be, or this 8701 is bad. That is actually more likely with this particular revision of motherboard. I'm just going to pop this chip out. I want to show you what happens if you try to run the system without any clock signal going into the VIC-2 chip. All right, so the system is off right now. The chip is out. When I turn on the computer, it's on, but we are getting absolutely nothing out of the video output jack. No video signal whatsoever. And that's, of course, because the VIC-2 chip generates the video signal that is output, the analog video signal that comes out of the system, and without any timing going into the chip, it's unable to even generate any kind of video signal at all. So if you aren't getting any kind of video signal out of your Commodore 64 at all, nothing, not just a black screen, but actually nothing at all, there's really just a few possibilities. Could be that there's no power getting to the VIC-2 chip. The VIC-2 on these earlier versions requires 12 volts and 5 volts, and there's a 12-volt regulator right here that generates that, and this 5-volt regulator, I think, also powers up the VIC-2 chip. It might only be used on the SID on this revision, I can't remember, but it's worth checking the output of both of these, which we'll do in a second. I'll just grab the multimeter so we can actually do that. But yeah, you either have no power going to this, maybe there's something wrong with the power switch, the power connector, the fuse is missing, this would affect the 12-volt rail, maybe there's a problem, in this whole area of the bridge rectifier, whatever, something, or even your power supply is bad. So that could be one reason. Another reason is you just have no crystal or clock, just like I showed you, get nothing, or the VIC-2 could be bad. But beyond that, it could also be a problem between the output of the VIC-2 and the connector. The luma and the chroma signal, that's the brightness information and the color information, makes its way into the RF modulator, and even if you're not using the RF output, that's then combined together into composite video, and then that is output from this connector. But if you have something like a multimeter and an oscilloscope, which this does both, you can check the voltages, and we can also check for the video signal itself. So let's just do that real quick. So I'm going to turn the computer on, and we'll get this into multimeter mode. And let's just check out the voltages that are coming out of this machine, out of these regulators here. So one side of this voltage regulator is the input. The middle pin is always ground, so we're getting 19 volts in. This is derived from the 9 volts AC that comes through the power supply. It's rectified, converted to high voltage DC, and ends up on this machine around 19 volts. And then the output of this chip is 12.1, which looks good. These can go bad, and then you'll have weird voltages, dead voltages, or too high voltages on there, and that can be a little bit of a problem. This chip here, we have 10 volts on the input side, and the output should be 5 volts, 5.07. Both of those need to be working for everything to be powered up, especially with the VIC chip. Let me just get the rest of this shield off here so I can talk a little bit more about what might be wrong. The RF shields, like on this machine, are only really used on later 64s. Some of the early ones just have a piece of cardboard. It's all pretty janky. A lot of times it's just been removed by previous owners when they open the machine to do upgrades and stuff like that. Going back to the troubleshooting process, I already kind of knew we had a good power and clock because I had that good stable video signal with the white line. So we already knew that was good, but I just wanted to kind of show that you can quickly test that. If you still aren't sure you're getting a good video signal, like you have no way to look to see if that line is there or not, switch your device into oscilloscope mode, which is what we have here. Get everything plugged in, turn on the power of the machine, and take a look at the pinout for the VIC-2 chip. And start taking a look at the signals on your systems. So pin 22, this is the clock symbol. It's like a circle with a line through it, and it says in. So we take a look at pin 22, and we see something, but it doesn't quite look right. This is not the best connection, and I think it's because our time base is wrong. Let's speed this up. And there we go. According to this, it thinks it's around 8.11 megahertz. I think that's pretty much correct. I mean, we're getting a good video signal. I can't remember exactly what it should be, but the fact is we're getting something there, and that will be coming from this chip. If this chip were bad or missing, then this would be like 1 megahertz or 0 or nothing, would be DC voltage. So that's a good way just to validate that we actually have a clock. Something else we should look at is pin 40, the VCC pin. That should be 5 volts going in. There we go, 5.2 volts. You could use your multimeter as well mode, but you can also do it here. It's not going to be the most accurate, but it's something. It's not like 2 volts. That would be bad. It's not 8 volts because that would kill the chip. We're at good 5 volts. Now you could also check some of these other chips while you're at it. So we'll just poke on this random chip, and it's at 4.9 volts. Now part of that is because I think that 5 volts is actually coming from this regulator. When we measured this, it was like 5 volts. I think that's what powers the VCC pin, but these chips are powered directly from the 5 volts from the power supply, which is a separate pin. So you really do need to make sure that you have 5 volts as well, because you could have a bad connection on your DIN, or the power switch could be bad. Some other problem could prevent the 5 volts from getting to the main chips, but it could still be getting to these because that's a different AC input that's rectified and whatnot. And that would power up the VIC and the SID chip, but not the rest of the system, which would obviously result in a black screen, which is exactly what this machine is doing. By the way, there are other clock inputs and outputs, like there's this one here, pin 17. That I think is the output that goes to the CPU. So it's worth checking those. We'll check those in a second by checking those on the actual CPU itself. These are all address lines. These are all data lines, IRQ, it's an interrupt line. We should have S-Luma. That's the main video signal information. All the sync info, everything is going to be on pin 15, and the color information is going to be on 14. So chroma, luma. So we need to check pin 15 to make sure that we have a good video signal. Okay, I had the triggering set to channel 2 for some reason. So now it's set to the correct channel 1, and now I have the trigger line on that white line. Now, if I zoom in a little bit, that's the white line on the left side of the picture, and then these are all the black pixels that we're getting because we have a black screen. If you had a system that had, say, stuff displayed like text and things, you'd see the level changing, and then it would drop down back to black, because on each side of a normal 64 screen where you have borders and you have text, there is a black section called the front porch and the back porch. So you always have that around the sync pulse, which is that right there. And then again, like I said, it's from left to right for the entire image. Now, if we zoom out, now we're seeing an entire scan line. So that's horizontal sync pulse, entire scan line, another horizontal sync pulse. And we zoom out far enough, those are the sync pulses, horizontal sync pulses. It's aliasing, that's why it kind of looks like that. But you see occasionally there's a pulse down here. That is the vertical sync pulse. Now, the reason why it's happening occasionally is because you obviously have 240 scan lines, and then you have the vertical sync pulse as the computer's telling the CRT to retrace. And we can't really trigger off that without having to hold off a more sophisticated trigger circuit, which this cheap thing does not have. But ultimately, we can see that we do have a good video signal on this scope. Now let's zoom back in so we can see our line. So yep, sync pulse, and there is our line. Now, if I turn the computer off and on, see it all disappears, turn it on, and immediately we're just getting the black screen and the pulse. This is confirming we have a good video signal. You should be able to see it on one of the pins on here that is the composite video signal. You're also going to see a color burst. That's the color information that's coming from the VIC chip as well. And that's just kind of confirming again that this entire section seems to be working properly. Almost certainly our problem lies over in this area on this machine. Now let's talk about the revisions of the 64s. There were a number of them for these bread bins, and then the later 64Cs, that's the more modernized case, looks like a C128. There were a couple versions in that as well. Typically this version of the board, which is the 25466, I think that's kind of when you want to look up the schematics for it, that's what you look it up by. This is the later one that's usually found in the 64C cases, those lower profile cases. And the reason why is normally there are 8 RAM chips. This only has 2 RAM chips. In fact, well, that was easy. That's our problem. So I've had this machine running for a while we were talking about troubleshooting, right? And you know, the 64 chips get kind of warm. VIC2 chip gets kind of hot. CPU gets kind of hot. The PLA, which is this chip here, it's 906114-01. These can get kind of warm. This one's not. This is the SID chip, so 6581, and that's always the part number on these older machines that have 12 volts for the VIC2 and the SID chip. That can get pretty warm, totally normal, and it's warm, but not that hot. Let's see about the CPU, 6510. It's kind of warm. The ROM chips, this one is unbelievably burning hot. And that might be a problem actually as well, because these get warm, but this one, that's like burns my finger hot. These are the two 6526s. These handle all the I/O, joystick ports, keyboard, floppy drive, and some other functions on the system. Now down here we have some general logic chip, multiplexers, things like that. We have the color RAM. This is what handles the color information on the 64. It's contained within this single SRAM chip. It's a 2114. These are super common. You can easily get these, but if you're having just color information problems, it could be this chip or something related to it. The VIC2 could be the problem, but the way it interfaces this to the rest of the system, this is only 4 bits wide. Anyways, these logic chips, if any of them are burning hot, yeah, that could be an issue, but none of these are even warm at all. The problem is these NEC Japan RAM chips. These 2 chips contain all 8 bits of the 64K of RAM on the 64. I call these 4464s. These are actually 41464s. A 4164, that's like a general part number for a single bit 64K chip. So 8 of them, 1 bit each, equals 64K on an 8-bit machine like this. Well, these chips actually have 4 bits each in them, so they are 64 kilobytes times 4. So you only need 2 of these for the entire 64K, which is why there's only 2 chips. That is not a populated chip, even though it says U11. It's never used on this particular revision. Now, when it comes to black screen on the 64, there's all sorts of things that can cause that, right? We get a bad ROM chips, you could have a bad CPU. I mean, basically, if any of this stuff is corrupting the bus, or the CPU is not working, or the PLA is bad, you can get a black screen. That's just the default state. If, say, you took every single one of these chips out, but you left on the system the VIC2, this chip, and the crystal, and all the power stuff, you would get that black screen that we're seeing right now. So if this was gone, you'd still have the exact same symptoms we have now, which is why troubleshooting the 64 can be a bit problematic, because sometimes it's just hard to figure out which chip is bad. We already validated we have a good video signal. I already know that we have a clock signal. What we didn't look at is the reset signal, because for a system to work, you really need power, reset, and clock. And you can check that on the 6510 CPU. You could take a look at the pinout for this chip and just use your oscilloscope multimeter to look to see if you have 5 volts on your CPU. So we already know we do because we checked it down here on one of these pins. You want to check the reset signal, and 6502 type CPUs are active in reset when the reset signal is around ground. So when you first turn on a computer like this, the reset input to this, that pin should be around ground for just a little while, half a second, a couple hundred milliseconds, and then go up to 5 volts. That allows the CPU to start executing code out of the ROMs and doing the normal things to boot the computer. If that reset signal stays low all the time, it'll never run any code. If the reset signal never goes low and you turn on the computer and it's just high instantly, the CPU won't run either. CPUs always need to be reset or held in reset when you first power them up, because the power on state of a CPU is kind of random. Without that reset signal being low, at least for a split second on a 6502 that is, it will never work. And as I said, the clock signal going into this needs to be good. Just for completeness, let's take a look at the pinout for this, because I don't remember off the top of my head, and let's check those inputs and see if those ones for the reset and the clock look good. Now the clock, by the way, it's coming from the VIC chip. And sometimes it's totally possible the VIC chip is working where it's generating a video signal, the black screen video signal, but it's still not outputting the clock signal to the CPU. Or perhaps there's a bad trace or a bad socket. Okay, so here's a 6510 pinout. Few important pins, reset. And the line over it says that it's active low, which means when the signal is at 0 volts or around 0 volts, the system is in reset. That circle symbol for the clock, and this is the output. The actual 6510 takes the clock input and also sends it out, and it's out of phase a little bit, and that's used for other parts of the system. So we're gonna have to check that pin 39 has a good clock signal on it. And there's the clock input, 0 in, and we need to make sure that also has a good clock input. That's coming from the VIC2 if you check the schematics. VCC, that's the 5 volts, that will be pin 6. And then of course there's all the address lines, data lines, and stuff like that. So we really need to check pin 40, make sure the reset is working good, and we're gonna check pin 1 and 39. Now the clock signal on a working 64 is around 1 megahertz, so we just wanna make sure that you have the time base set correctly. 50 nanoseconds is obviously a little too fast. So let's slow this down. I can't remember what it should be, but you just have to make sure you're not looking at it wrong. There it is, 1.03 megahertz. That's the input. That was the pin 1. And the output, remember, was 39. And that looks good as well. It's a little smoothed off looking, but that's completely fine. That was just the oscilloscope being stupid. And we can check our reset, which is currently sitting at 4.9 volts. Now what we need to do is we need to take a look at that reset when I turn on the computer. So I'm gonna go back onto the reset, and we'll turn off the computer. And when I turn it on, it should stay around here for just like half a second and then go up. Here we go. Yeah, like instantly to 5 volts or stuck at down there. And then that's something to be concerned about. This is just stupid. There's just something wrong with this. So ignore all the weird glitches you see. That is just this dumb probe connection here. It's just bad. I don't know if I think it's the probe. It's not the oscilloscope, because I've used other probes. It's fine. It's this really junky probe, which might have been one that came with it. Look, just turning it made it more reliable. And now we shouldn't see those glitches. There we go, came out of reset. So that's what normal reset should look like, but it could be a lot faster. Like it could just stay down for like 200 milliseconds and go up, be fine as well. But this is like a second, no problem. It just slows down the boot process on the 64 a little bit by taking a second to go up. So we've really done the initial basic troubleshooting on all 64s. It's pretty much universal between all of them, especially these bread bin looking ones with these full-size motherboards. The later small motherboards, instead of using 12 volts, only use 9 volts on, I think the SID and the VIC, or I can't remember which one it is. But these earlier ones, they always have 5 and 12 volt regulators. You gotta check those, which we've done. And then we gotta check for the clocks, which we did, and it's good. We have a good video signal coming out of here. And we also have all the necessary stuff for the CPU to start executing code. Next thing I would really recommend doing whenever you're doing any one of these 64 troubleshooting is just let the computer run for a little while. If you're getting a black screen like this, you don't even need any special cartridges, and you just start feeling around. Now, as I mentioned, ow, that is so ridiculously hot, that chip. And the other problem is the 2 RAM chips are absolutely, positively burning hot. This is bonkers how hot that is, though. That is not correct. I mean, I think I just burned my finger. VIC2 chip, it's warm, but not too hot. Yeah, SID's looking good. I mean, things are all fine. It's really the RAM chips that are suspicious. They should not be hot like that, especially not this machine. Because if we take a look at these chips, they're from 1986, 13th week. These aren't even like early chips. These are later chips. They tend to run cooler. Other date codes, 86, 19th week, kind of tells you when this machine was built, right? We just look for the latest built chip. 27th week, 27 is a really burning hot chip there. 24th week, 24th week, 27th week, 27th week. So I'd say this was built at least middle of 1986, which for a bread bin machine is pretty late in the life cycle of a 64. I'm not convinced that this board, which actually is held in by one screw in the corner here, a couple screws, looks like it's got one over there too. So it's pseudo held in, but I have a feeling this was swapped into this case. And incidentally, look at that, broken there. I'm thinking this was swapped into this case. And I wouldn't be surprised if this actually came from a machine like a 64C, the later case revisions. I've worked on quite a number of 64s by this point, so I have a good amount of experience. And I happen to know that these NEC 4-bit wide RAM chips that are on here, which are commonly used on the short board, which is a motherboard revision from the 64Cs that's just a lot smaller, it probably only comes down to here. So this bottom section of the board is cut off and things are rearranged. The chips are a little bit different, but it always uses 2 of these RAM chips for a 64K. And when they're the NEC ones, they go bad. They absolutely go bad. Now, is it the RAM chips that are bad that are causing this character ROM generator? So this is the basic ROM, kernel ROM, that's like the main OS of the computer, and character generators. This is what holds the 64 character set, is this chip. Well, is this chip hot because these chips are bad and they're trashing the whole bus? Or is this chip bad and causing the RAM to get hot? I don't know, but we can tell for sure there's something wrong. Now, if we plug this back in, and let's get the scope hooked up, and using the pinout for the CPU, let's take a look at the data lines. Now, there's all the address lines and the data lines, and on the 64, all the data lines, all the address lines are pretty much all connected together. The RAM address lines are not connected directly to the CPU because it has to go through multiplexers, which are some of the logic chips that are around the RAM. But all the address lines that go to the ROMs, to all the other chips are directly connected. So definitely if some chip is malfunctioning, it could be killing the address lines and data lines that it has on it. Now, there are more address lines on the CPU than there are on the ROM chip, for instance, because this ROM is, I think, a 2K chip. So we have address lines 0 through 15 on the CPU. So there are 16 address lines for 64 kilobytes of RAM. But this chip here only has 2K. So it's only going to use like the first 2K worth of address lines. But it's possible this chip has gone absolutely bonkers and is killing or trashing the address lines and all the data lines. But it's also possible, and kind of likely, because that's the experience I've had with these NEC RAM chips, is that these go wild and they trash everything as well. So they trash the data bus. They hooked up to all 8 bits on those data lines that all the other chips are hooked up to. So I'm thinking what we should do is take a look at the data lines with the oscilloscope and just see exactly what they look like. And there is our first data line. Now there's activity, but it doesn't look correct. Should be going up to like 4 volts, 3.8 maybe, 4, 4.5, even 5 volts, not 2.5 volts. So something is wrong on that line. And they're all going to look like that. Yeah, they're all going to be messed up looking. I mean, look at this one. That one's barely able to do anything. Make sure I have a good connection on these pins. Yeah, I mean, it's trying. I'm just going to slow this down a little bit so we can see a little bit more what's happening. It's trying to do stuff, and it's just not able to. So that's not normal. It should be going way higher up to here. So that one, same thing, 2.3 volts. That one's at 2.8. And that one there is like also barely able to do anything. So something is super duper wrong with this machine. Now, the thing is, you can't just immediately assume that these chips are the culprit. The PLA, which on these machines, think of it as the traffic control cop. It is what selects all the chips. It turns on the chips when they should be turned on and turns them off when they shouldn't be talking. So if the CPU is trying to read from the kernel ROM, it sets up the address line to say, hey, I want to read from where the kernel ROM is located in memory. And then the PLA detects the address line configuration and goes, oh, okay, CPU, you're trying to talk to the ROM chip. So I'm going to activate the ROM chip. So the ROM chip turns on, as a chip select line, turns it on, and they can start communicating back to the CPU over the data bus. And then when it's done and the CPU goes to read from the RAM, it'll turn off that ROM chip and it'll go to select something else. Well, the failure mode that often happens on PLAs is that they kind of fail internally, where some of the chip select lines that go to turn off and on certain peripherals on the computer, on the 64, get stuck, and those chips turn on all the time. So even when the CPU is not talking to the ROM chip, that ROM chip is activated, it's turned on, And then, well, of course, that's going to cause a bus conflict because two things at the same time are going to try to talk on the bus. Like the CPU will try to read from the RAM, but then the ROM chip thinks it's trying to read from that as well. And both of them will try to talk on the bus. And that can create excessive heat because you have two things conflicting with each other. Like one thing is trying to pull it to the 0 and one's pulling it to 5 volts. You know, it's causing a conflict like that. So before I take any of the chips out on here, I really need to make sure that the PLA is working correctly. All of its chip select lines that come out of it are not conflicting or not stuck at low values that would turn on any of the chips that they shouldn't be turned on. Now, I was thinking that we did check these data lines and they were all messed up looking. So there's definitely something wrong. That could be easily caused by the fact this ROM is completely died and shorted out internally, or it could be caused by the fact that the RAM chips have done that too. Because again, these are suspect, so is that chip. They're both suspect. But what we need to do, I just realized, is check the address lines on here. Just make sure that those are working correctly. They are going up to like high and low as needed. And that's when the PLA can then select which chip is active all the time. Because if those are looking screwed up, because they could be, because this ROM chip could be dead, or, well, somehow the RAM, I don't know. We should just check that to make sure, because the PLA can't work properly without address lines that are working correctly. Okay, so I'm starting here on pin 7, address line 0. There we go. That looks normal. It's 4.8 volts. That's how the data line should look as well. So we'll just quickly look through these. CPU is trying to do stuff, and it's just unable to. And I have to watch out not to burn my hand on that ROM chip because it gets so hot. So I'm holding my hand away. Yeah, but this all looks normal. You know, we're looking for voltages that are down at like 2 point whatever, just like it was with the data lines. But all of this looks fine. Fine. And there's 2 more on this side. Yep, that's good. That one's good. And don't worry about the fact it has these little angles. That's completely normal. Okay, so we'll take a look at the PLA, the 906-11401. That's the PLA for these older 64s, well, all of these bread bin ones. And when you look at this, you see all these I inputs and you see these F inputs or outputs. It's these F outputs that are the ones we need to look at. Now, if you look at the schematics, you can see which go to what on the motherboard. Like, you know, one goes to that chip, that chip, that chip. But we just need to check all of these to make sure they're all good. F0 all the way to F7. We got to check them all. 10. Okay, so I'm on F7. So when I turn on the system, we should see either this line stuck high, so not at 0 volts or anywhere near there, or it should be going up and down. Okay, so it's high. So that's fine. The system's not really executing any code, so you're not really going to see a lot of activity here because the whole computer's just dead, right? But all of these outputs should basically be high except for maybe the kernel ROM. All right, so there's one that's actually active. I don't remember which one this is, but it's doing stuff, which again is normal. You just need to make sure that it goes, well, it's going up to 4.1 volts, totally fine. It has to be higher than like 2.5 or so to be valid TTL. Here's another one, 4.1, fine. That one there looks fine. It's not stuck. And that one looks fine as well. This is going up to 3.2. Okay, actually that is F0. That was F0 we were looking at. Let's look at that again. It's kind of low, but if I zoom in a little bit, it's going up to 3 volts. So I'm going to say that's fine. TTL, usually if it's above 2.5 volts, it's fine. 3.3 volts is valid high for TTL logic, which is what's on this computer. So that's a little out of spec, but I don't think that's enough to cause a problem. I did a quick Google just to figure out what the pinout was for the character ROM, which happens to be this one, which we know is getting really, really hot. And it's the chip enable line, pin 20. That is the line that is connected to the PLA. Not sure which pin it is, but let's just check what that line is doing on here. If that line is stuck up around 5 volts, that means this chip should never be turned on and it should never get hot like that, like it is on this machine. Okay, it's occasionally being selected, but only occasionally. So there is no reason this chip should be so burning hot like it actually is on this machine. None at all. Now I mentioned that the address lines are connected to all the various chips on here, but they're not connected directly to the RAM. The data lines are though. So what we can do is I want to do an experiment, and I'm going to cut one of the pins on the data lines on the character ROM first without cutting them on the RAM chips, because I'm pretty sure the problem is either this or both. It's probably both, to be honest. I'll go on record saying it's both. But let's do an experiment. Let's pick data line 3, which happens to be this bottom corner. And I'm going to use these cutters to cut that pin. So what we need to do first, let's just validate to make sure we can see what it looks like before I do the cutting. All right, so data line 3, we turn it on. Wow, okay, so that one is super screwed up. Like, it's barely working. So what I'm going to do is I'm going to cut that pin about halfway up. That means that I can reconnect it if I need to, because there's going to be some part of it stuck in the motherboard and there'll be some part of it stuck in the chip. But there, it is now cut. And if you take a look, and you can just, it's hard to see, but it is actually cut. You just have to look at it at an angle. It is not connected anymore. And the reason why I did that is it's going to allow us to probe the lower part that's down on the motherboard to see if that data line is now working correctly, or we can probe on the top part to see if what's coming out of the chip is correct. So let's start on the top part here. Okay, yeah, nothing. Now let's move to the bottom part. Aha. Yeah, how interesting. It's still not working correctly. So data line 3 is still very, very, very trashed. But the weird thing is that when we go onto the top part of the chip, we don't even see any activity at all. Yeah, there's just nothing happening. I mean, it goes up a little bit. So see the line there? When I turn it on, it moves up a little, but that's it. And there is some activity on here. Remember we saw chip select, which is chip select line. There, that's the chip select line. So it's being activated. It should be trying to write to the bus, but it's not. All right, so let's go take a look at 4464 RAM pinout. Now we are looking for data line 3. Now the problem is we don't know which chip is connected to data line 3. And because each of these chips has 0, 1, 2, 3. So there are two possibilities for data line 3, that one, being connected to two different chips. So all we need to use is the continuity mode. And now what we can do is just make sure we're in the right mode. We are. So I'm touching to the pin that I cut, but on the motherboard side. And it should be one of these pins on the RAM chips here. Okay, there it is. So it's that one. And it's not going to be that pin on this chip. It's only going to be on that one. And the reason why I want to do this experiment is I want to cut the pin on this RAM chip in exactly the same way, kind of halfway up. So make sure the computer's off. It is. There we go. That is cut. And the reason why I want to do that is now I want to do that same experiment where we power it on and we want to see if the data line 3 is no longer trashed anymore. Because I suspect that the RAM or the ROM or both are bad. And it was my suspicion that one of these was trashing the bus. And the only way to really figure it out is we could either remove these from the board or we could just cut these pins. And cutting the pin is not a big deal because all you do is take your soldering iron with some solder and you can re-bridge the pin that I cut. So if it turns out the RAM is the only problem, there's nothing wrong with this, then we can just put the pin back that I cut here and no one's the wiser. I mean, you'll see a little blob there, but no big deal. Back in the oscilloscope mode, I'm going to probe on the bottom side. That's the motherboard data line 3. I can also do it on the CPU, but I just don't remember what pin it is. Let's do it there, and let's see if this has normal activity now. Yes, fixed. So we can zoom out a little bit, and there we go. Maximum 4.3 volts. That is normal looking activity. So pretty much confirms that that RAM chip is bad and it's totally trashing the bus. And I'm going to go off the assumption that both of these are doing the same thing. And that comes from experience because I know these NEC 4464s are crap and this is their failure mode. So I'm just going to quickly reconnect the pin that I cut on this ROM chip. Make sure this is actually connected. Because I really want to know if this chip is also trashing the bus. Because now that this is reconnected, when I touch the top part or the bottom part, it's just all one, and I turn the system on, we should see the same exact activity on the oscilloscope that I just saw after we clipped the pin on the RAM chip. So here we go, 3, 2, 1. Yeah, that looks normal. Well, I'll be. So I don't necessarily think there's anything wrong with this. I don't know why it gets so hot though. I'm still very suspicious that that chip is not working correctly. But I can tell you without a doubt that these two RAM chips are bad and I'm going to be removing them from the board right now. Now, of course, removing chips can be problematic. And one way you can go about doing it when you have a chip that you know is bad is you can just cut all the pins, pull all the pins out with your soldering iron and some tweezers, and then you can use some solder braid, which is like this stuff here. This is good quality stuff. And then you can clean out the holes, install sockets, put new chips in. Because I do this a whole lot, I have one of these Hakko FR301s. This is a great device that will allow me to quickly get those chips out. And I have a video, which I'll link below, that has to do with how I take chips out of boards. It's a combination of the Hakko 301 and some hot air, and that just makes sure you don't accidentally ruin the board. It's very easy to damage 64 motherboards since the traces are so very thin on them. But in the case of this motherboard, one thing that you will need to do is you also need to get the shield off the bottom, because we can't desolder or anything with that on there, obviously. If you don't have a way to easily desolder something that can suck up a lot of heat, hot air plus a soldering iron can help. You can use something like this or a blade and just cut through the shield. It is just like really thin kind of metal. For me, I'm going to use this, which has a lot of thermal mass and has no trouble getting this off. And the only thing I do is once this warms up, I use something like this pick, and I can just pick the thing, apply heat, and then try to open the little tab. One trouble spot for me is this one in the middle. I can't really get my desoldering iron in there. This thing is just too bulky and it starts to melt the connectors. So I usually just leave that to the end, and I use metal fatigue to get that one off. Okay, so all those tabs are off except for the one there in the middle. And this should just sort of come off now. There it is. And as I said, the one that's in that spot, it stays connected. So I just kind of metal fatigue it away. Or you could just use something like these flush cutters and just cut that tab off. Okay, well, let's take a look at the bottom side of the board. Let's look for any signs of rework. I'm gonna say nope. I don't think this machine has ever been worked on. It is in pretty nice shape with flux. This just comes from the fact that these components are hand soldered at the factory. All right, so we're taking out these two RAM chips, right? So sometimes it can help if you aren't used to what you're doing here is just grab a Sharpie and draw. Oh, it's actually there and there. So you want to just make sure you're desoldering the right 2 rows of pins. So it's those 2 rows right to there. Yeah, sometimes you really have to clean out your desoldering iron because that's not going to work. All right, I've done pretty much all I can do. I'm gonna use hot air to get these chips out because they will not come out. If you try to take these out now, it will just rip traces, especially because you can see there's still a good amount of solder on some of those pins still. Hot air would have helped if I applied it while I was working on it, but it doesn't matter if you apply it then or you apply it now. It's sort of like 6 of one, half a dozen of another. So I have this set for 350 degrees Celsius, and I'm just gonna apply a bunch of heat onto the board here. And I'm going to use this pick to try to get under the chip and then gently lift it. Wow, this is being extremely stubborn. This is wild. So if it's doing this, I sometimes just try to focus on one side specifically, and I'll then work on the other side. I mean, this is acting like I didn't even desolder it at all on the other side, which is ridiculous. I did. The chip is moving a little bit, but it's just stuck. All right, I've had it. This chip is just getting cut out. So I'm just gonna cut this and be careful because it's hot, of course. Yeah, these are good Nipex cutters, but they're not that sharp. And sometimes it's better to use these cheapy ones because they have much sharper tips so you can get in there and really cut the legs. Some of the pins were already out on that one. It's just a couple of them were very stuck and being stubborn. Okay, there we go. 2 dead RAM chips. So I don't know how many chips I have desoldered from boards, hundreds and hundreds, and yet even I get stuck sometimes, like I just did with this thing. Unfortunately, this desoldering process, that pin was already loose, it's a bit of an art form, and as you do it more, you will just get more experienced at it. So if you're a beginner, unfortunately, it can be very easy to cause damage to the board, and those tweezers are useless. Let's try a different set. So I'm just applying heat, and then those pins should come out. Well, that didn't really go to plan. I don't know why, but something weird was going on with this board. Just getting those chips out was nearly impossible. Even after I cut the legs, just getting the pins out was so difficult. It feels like the vias were kind of self-destructing. And you will notice that I actually ripped a trace, that one. And that happened not from me lifting the whole chip out, me trying to get the pin out that I had already cut. I just couldn't get it out of the board, and I had to use so much heat that it did rip this trace, which goes to that pin right there. In addition, some of the vias are just looking a little worse for wear. So what I need to do is double check after I'm done Well, I'm going to have to add a bodge from there to there on the bottom side, but this one looks bad as well. So I might need to, well, just double check that everything is all connected together once I put the sockets in. And unfortunately, sometimes that is just how it goes. And I have never struggled so much to remove a chip from a 64 ever. And I'm not even sure how many 64s I've fixed over the years, but this was oddly the hardest one to get those two chips out of. Very strange. Okay, so there are two kinds of sockets. These are cheaper, but unfortunately they're just terrible quality these days, and these aren't known to be great either. But I tend to prefer this type, the one with the round holes. One of the reasons is if the vias are a little bit kind of messed up, these ones seem to make better connection in the board than these. These are sort of flat pins, and sometimes they get bent. So we'll bend that one back into shape. Let's see if this fits into that hole without any issue. Okay, yeah, that fits in fine as well. So let's see, I'll put two of that type into this board. Before I install the socket though, I know 100% I need to double check that that pin is connected through, and I know for sure this one is not because the trace actually got ripped. So I'm going to put marks here just to help me remember where I need to check to make sure we have continuity between the socket here and the same pins in this one. Those are just parallel signals. So let me just quickly solder these in, and then we'll check for continuity and add the bodge wires. Okay, we have our multimeter probes in continuity mode, and let's just double check that everything is connected through. So that was the first one I thought I was worried about, and it is fine. And what I like to do is alternate the connectivity just in case there's a short. Now the data lines are not connected through, so that's not connected, that's fine. That one wasn't connected, and I think there's two more on that side. These should be connected. That should be connected. These will not. I think that's data lines. I guess that's connected, and maybe this one's not. Yep. And then we're here on the broken one. This should be connected, and it's not. And let's double check the rest of these. So I think we just have one bodge wire I have to add, and I'll use the probe again. It is this pin right there. That pin should be connected to that pin. So anytime you change out sockets like this, especially if you're not really experienced at doing it, I would always double check the pinout. And of course, if you're changing one of these chips, you can use the schematics to see what each pin connects to, just to make sure that you didn't accidentally lift a trace. I've worked on so many Commodore 64s that people have tried to repair before, but then they took a chip out and they didn't realize they lifted a trace like I just did, and they didn't fix it. So they put everything back together, the computer didn't work, and then they gave up on it, because trying to fix those types of problems, if you don't know what to look for, can be really, really difficult. And double checking, yep, it's not connected, but I think this one should be, and it is. Oh, I didn't even solder that pin. I missed that one. Well, I gotta fix that as well. And that one is connected. Okay, so I gotta fix that pin, and then I have to add a bodge wire from there to there. This little unconnected or unsoldered pin, kind of insidious, because I think it was making a connection just because it was pushing on the side of the via, but it would have been intermittent. So possibly that could have caused future problems if I hadn't have noticed that. I'm just gonna spend a moment to kind of clean up the flux a little bit. It's making sure I don't undo the bodge wire that I installed. It's funny, I'm not sure why that red Sharpie mark didn't come off. I had 3 and they all came off except for that one, oddly enough. And this is 100% IPA that I'm using here. Okay, well, doesn't look perfect, but looks better than it did at least. And now we can double check on this side to make sure that our connection was made correctly, and it is. So 5 up, there's that black mark. That is currently connected through, and we'll just double check that that one is still connected, which I think looks dodgy, but it's connected. And I think that was the one that I hadn't soldered properly, the one right below it. Or maybe it was the one above it. No, that's a data line, I think. Okay, now I gotta find some chips to pop in here. I have some stock of chips. There's a couple more of those NEC chips. It's got a tick mark on it, but let's see what the original ones look like. These were dash 15s and from 86, and these ones are from 85. There's another 85 one there as well. I'm not sure where I took those off of. Might have been like a video card or something. So I'll just use 2 of these 120 nanosecond chips. And if they ever go bad in the future, whoever has this machine, they can just pop those out since they will be in a socket. Of course, this machine can easily have other faults, right? We could have a problem still with this bad boy. And just for completeness, we'll put X's on these. I mean, it's a given these are bad since the legs are all cut off, but just, you know, that's what I like to do, right? Everything looks good. Chips are in the correct orientation with a notch facing up. All right, here we go. 3, 2, 1. Did this cause it to work or fail? Still not working. So those chips are not getting hot. And the character generator is still absolutely burning hot. So what we need to do now is we could try running like a DesTest cartridge or whatever, but let's skip that. Let's just take a look again at those data lines. So 37 all the way to 30. Okay, best pin 30. I'm starting from the bottom. That looks normal. 31, 2, 3, 4, 5, 6, and 7. Wait, is that really 7? 7, 8, 9, 10. Yeah, that doesn't look right, does it? Aha. So 7 is still acting up. Just double check that, yeah, data line 0 is 37. Aha. Ow, yeah, don't touch that chip. Well, I'm thinking that we should check the character ROM because it's the one that's getting super hot, and we should take a look at data line 0 again. So pin 9, which I just put a little mark on there with the Sharpie. So we'll just double check that is the one that looks suspicious. Yes, very suspicious. Okay, what I want to do now is instead of just cutting that line, which should work, I want to test out a little bit of diagnostic kit that I recently was given. This device is called the CurveBug, and it was created by someone at the VintageTek Museum here in Portland, well, Beaverton, Oregon. And what this can hopefully allow us to do is hooking these leads up to, for instance, the ground line or the 5-volt line and the data line 0, the one that's suspicious. We could compare the way the signals look on this to the other pins. And we would do this with the system powered off. This actually injects just a little bit of voltage, like microvolts range, into the system under test. And then we can hopefully see a difference between data line 0 and all the other data lines. And that actually works for things like chips, like this bad RAM chip. We could compare this to, if I grab one of the good RAM chips, one of the NEC ones, we can maybe probe around on this and see if this looks suspicious. It can help you potentially diagnose bad chips, bad parts of the system by just probing around. And I think I'll do a better job at explaining it once I give this a try. So I have the CurveBug plugged into a USB port on my lab PC. It's just USB-C connection. And there it is. This is the program that's running. And we have a red and a black trace because we actually have black and red. We have 2 inputs on here. So I'm going to take one of these good NEC chips. I'm going to hook on the common onto the first pin. And I'm going to hook the red line onto the second pin, because these are pins that are still available on the chip that I cut off the board. Now there's the red trace. And it's interesting because it's kind of moving around on its own. And I'm not sure, that is my hands that are actually doing that. So I move it closer, you know, it goes up. So it's a very, very sensitive device. In fact, let's move this out of the way, the oscilloscope, get that out of there. Maybe that's causing noise. There, actually, that kind of got rid of the noise. So yeah, I guess that was affecting it. So anyways, that's the good part. And you see the way that trace looks? Let's plug it into the bad chip. Same 2 pins, and that looks a little different. Is that a problem? Not sure, but maybe it is. Now, just to sort of show you what this does when you connect the 2 leads together, you get a vertical line. And that's telling us that we have basically no resistance. I just hooked up a random diode that I had sitting on my bench, and you can see that the way the diode is hooked up, the red line now kind of curves downward. Now let's flip it around, see if that changes the other way. It's actually very similar to the way it looked on the chip, right? The red trace just goes whoop, goes straight up. And that's compared to if I disconnect it, then it just goes straight across. Now I'm just going to grab a random resistor that I had laying on the bench, and we'll hook that up. And instead of a vertical line, it's actually slightly slanted. Let's try a random diode that I had sitting on the bench. That way, it's just doing nothing. It's not lit up or anything, but it doesn't read anything. But let's flip the leads around. And there we go. We're getting a curve. But instead of being over here, it's way over there. So this has probably something to do with the breakdown voltage or something. It's not like the LED's lit up, so it doesn't have enough voltage to do that. But it does look different than this diode. But if this diode were shorted and I hooked it up, of course, we'd have a vertical line. I just grabbed a random resistor, and this one has more of a slanted line. I'm pretty sure that the closer you are to 0 ohms, the more vertical the line is, and the closer you are to like meg ohm, the line will be straight, but kind of this direction, very flat against the black trace. Now, if I plug the probes into the black connection on here, the black trace will be doing this stuff. The reason why it has 2 inputs is because you might want to compare 2 chips to each other, or 2 different traces to each other. All right, next thing is I grabbed a capacitor, and the vertical line, instead of being over here, which is close to the 0 point, which if I connect them together, you can see it's on top of the green plus that's there. Now it's over here. So it's just showing us what a capacitor looks like. And if I reverse this, let's see what happens if I reverse it. You saw it actually moved a little bit. Now, the last thing I want to hook up is, here's a random inductor. I think I took this out of a TV or something, monitor, whatever. Let's hook this up. Vertical line. So that just basically looks like a dead short. And an inductor does. Looks like a very, very low resistance resistor. Okay, so back to these chips. So looking at the pinout for the chips, pin 18, that's the one I've been connecting the common line to, is ground. We could also hook up to pin 9. 17 was one of the data lines. So if we connect back to that first data line, that's what data line 3 looks like. Let's hook up to the CAS line. There's the CAS line, so that looks like that. And that's data line 2, D2. Now, while I have it on data line 2, I'm going to move the common pin, or the common connection, over to the VCC, or the 5-volt pin. And it looks like that. Okay, so what I'm going to do is I'm going to actually connect an extra set of probes so we can use the black input to test out this other chip. So I'm hooking up the good working chip. So the good working chip, I have it on the ground pin, and I have it on data line 2. And I'm going to do the same on the bad chip. Wow, it's so sensitive right now. If I just like put my hands near it, it's changing. I'm going to just move this 64 out of the way. Okay, that's better. I think the 64 there was like causing some stray capacitance, inductance, or whatever. It's not moving around anymore. So red trace, good chip, black trace, bad chip. It looks different. Is that smoking gun that it's telling us that this bad chip is bad? I don't know for sure. Well, let's try a different pin. Let's move to the CAS pin. Red trace is the CAS pin on the good chip, and the black trace is the CAS pin on the bad chip. They look different. Why don't I grab another one of the good chips and we'll just compare them directly. I think I have another one. Yes, I do. This one right here. So we're going to hook this one up. This is the red trace up to the CAS pin again on another good chip, just to see if it looks exactly the same as what we were just looking at. Yeah, it does. I'd say the red trace is pretty much a match. There we go, data line 2 with that big circle. Now what we could do is I could try to probe the other bad chip. Okay, that's the other bad chip, black trace, data line 2. Also looks very similar to the other one. Why is it moving around? Is it just my hands? Oh yeah, it is sensitive if I touch it. But pulling my hands away has that bigger loop. Put it on the CAS pin. CAS pin on the bad chip there looks very similar, I think, to the CAS pin. Well, no. The red trace is the good chip, and the black trace is the bad one. Okay, one thing I want to try is with the red trace, I'm going to hook it up to basically VCC and ground. So that's just hooked up to the negative and the positive pins on the good chip. And let's see how that looks on the bad chip. Now, unfortunately, I'll have to hold this on here because the positive pin, the VCC pin's almost gone from the bad chip, but check that out. It looks very, very different. We have to assume that that's maybe that heat generation that's coming from the chip. So I think what I want to do is I want to probe around the actual 64, and I want to take a look at data line 0 and data line 1 or any other data lines. And I want to try to see if this CurveBug will reveal any weirdness happening on data line 0 versus all the other pins. Because we can clearly see the data line 0 looked different on the oscilloscope. But say we didn't have the oscilloscope, we just had this CurveBug, which is a very inexpensive little device. Maybe this could help us identify which of those lines is kind of messed up. Okay, so I have the ground lead hooked up to the RF shield. All right, so let's first start by checking out data line 2, which is, well, the one pin off the bottom. That's data line 2. Okay, looks like that. Data line 1 is the next one up. Looks like that. Data line 0. Well, there we go. That's obviously bad. That is obviously bad versus the others. So CurveBug showed us there's something wrong with that data line. We already kind of knew because we could see that on the oscilloscope mode when the system was running. But even with the system off right now, we're able to see a problem with CurveBug. Let's check the resistance though. Let's see. I'm assuming we should be able to see an issue in the resistance mode when we take a look between ground, and let's do those data lines again. So that's data line 2, meg ohm, data line 1, meg ohm, data line 0, 37 ohms. Okay, so clearly that's wrong as well. So our question is that coming from this chip or is it coming from something else? Well, let's get cutting. I'm gonna grab some cutters and I'm gonna do the same thing we did before, which I'm gonna cut that one pin sort of halfway up. And the reason why I'm picking this chip, by the way, is because I suspect this chip gets getting super hot. If this chip wasn't getting super hot, then you might have to just do this cutting exercise on all of the things that are on data line 0. So we know it's not the RAM, you know, it's not going to be the CPU, not most likely. It could be actually, but it's not likely. You know, we could try cutting it here, 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 you know, on these. You just kind of go through a process of elimination, try to figure out which chip on data line 0 is causing this resistance fault. Let's use the multimeter to check resistance in 2 places. So I'm going to check on the pin on the top part of the pin, the part that's on the body of the chip that's cut, 37 ohms. If we go down to the motherboard, 5 meg ohms. Well, there you go. That chip is the problem right there. And with CurveBug, we'd obviously see exactly the same thing. But what's cool about CurveBug versus just using this is, well, yeah, in this case, this was all I really needed to find the culprit. Well, with CurveBug, you can see inside of chips, you know, where we had those signals that were kind of looped and the loop was bigger versus smaller, like the bad RAM chips versus the good RAM chip. And that could help you identify a bad RAM chip, for instance, if you had several out of the system. Well, we could test them one by one. Looks the same, looks the same, looks the same. Oh, something looks weird on like 1 or 2 of these chips. Well, mark them as suspicious and go from there, because we're actually looking at what maybe is inside of these chips. And same could be said for, say, a PLA that has a bad output. Well, that's the PLA. If we take it out of the board and you were probing around with the CurveBug, potentially the output that's always activating one of these chips, like it's stuck low, would look different on here versus all the others. It is my assumption right now that theoretically this system could work with that leg that's cut, because I don't think there's a problem with the rest of the pins on the character generator. I think it was just the one that we cut, data line 0. And now that I cut that, I think the rest of the system can actually run if the rest of the system is good. So here we go. I have it plugged in. That leg is still cut. I mean, we're going to have messed up characters on screen, but let's see what happens. Yes, there we go. Now, the funny thing is, I would expect us to see mostly normal letters. So I feel like this character generator is just, it's still totally screwed up. And it's still burning hot, even with that data line disconnected. It's just that the rest of the data lines on this chip are not crashing the bus, are not ruining the data bus, which prevents the system from executing code from the ROM and the RAM and stuff like that. So the chip is still bad, but cutting that data line was all we really needed to get the system actually booted. And as you can see, it boots. Now what we could do is plug in another cartridge, like say the Easy Flash, because I don't think it uses a character ROM. I think it will generate its own fonts or whatever. Let's see if that works. Yeah, there we go. So it's not using the character generator, and this just proves that the rest of the system is working. The character generator ROM basically has the character set for the 64 in it, but cartridges can load their own characters. Obviously, the font that we're looking at here does not look the same as the normal character generator. Therefore, this just uses RAM. It loads basically its own character set into RAM and tells the VIC, use that character set, which is why it works. But we saw garbage when it first powered up because the character ROM is still bad on this system, but I knew that the system would work when we actually put another cartridge in. What I should do is grab some kind of a diagnostic cartridge. All right, we'll try using Matt Desmond's DesTest switch. What this does is it has some extra circuitry on it to allow it to first test the first 4K of RAM, just like the regular DesTest, which is like a dead test, but better. But then this can do a kind of a soft switch into a normal 64 mode, where this can then test all of the RAM. I can't remember if this is actually out yet. This has kind of been in development for a while. Matt Desmond gave me one of these a while back, but let's give this a try. So what this does is it will first come up, it will first test, yep, it doesn't use the character generator, so that's not gonna be a problem. It'll test the first 4K, C64 max mode. So it's in max mode, which is like the same thing as what dead test runs in. That can only access 4K of RAM, which is why all the RAM tests there say 1 to 4K or 1 to 2K, et cetera, et cetera. This is using a really, really solid RAM test that basically do the March testing and really, really thorough RAM testing on everything in the first 4K, including the color RAM, which is what's happening here. That's the 2114 chip I talked about before. Reboot itself. There it goes. And now it's in full RAM test mode. And now it's able to test all of the RAM. So first it does a 0-page and a stack test, which is the little first section of memory. And then it's going to test from 1K to 64K. And this takes a bit longer, but it's a super duper thorough RAM test, March testing. Pretty much the best RAM testing that you can have. Oh, it's saying the character ROM is bad. Yes, right there. Character 0063F8, whatever. It should be in green letter. So that's telling us right there the character ROM is bad. But hey, we already knew that. But I bet you this computer, at least when it comes to this part of the test, is going to be working. Now, of course, to do a complete diagnostic on a 64, you need a test harness and another diagnostic cartridge that tests all the I/O and whatnot, but you don't necessarily need that. If you have other peripherals, you can plug a disk drive in, you can plug a tape drive in, you can plug joystick in, a keyboard, you can listen to the music, you can pretty much test everything on a 64 by just using it. But if you're trying to turnkey test a bunch of them, like I might have to do, just plug the harness in, boom, it tests everything. It's real easy to kind of get something out the door. So while this is running, I'm going to have to find another character ROM, which I know I have somewhere around. So that's not going to be a problem. I can put a new character ROM inside this machine. I will have to desolder it. Hopefully I don't have as much trouble as I did with the RAM. Luckily, from my understanding, 6581s, which is the SID that's in here, is one of the more reliable of these early SIDs. These AR ones, this one's made in 1986. Seems like by then, MOS had like figured out the process to make SIDs more reliable. I'm not sure I've ever had a 6581 R4AR that has had any kind of failure. So we're looking good with this machine. Obviously, we don't know the I/O works. You know, these 6526s can have trouble if like someone zaps the joystick ports with static electricity. That's one issue. If you're holding the 64, you can touch the side. That could zap it, could kill the keyboard. The same thing for the user port and stuff like that. But when it comes to character ROMs and the failure like this one has, where it's like incredibly burning hot, that's not super unusual of a failure mode. I've definitely seen that before. And usually, like I said, the ROM chips get warm, but if one of them is extremely burning hot, that pretty much confirms to you that there's something wrong with that chip. And you might as well just change it, take it out, and then see if the machine works. DesTest can work with no character ROM installed, no basic ROM installed, and no kernel ROM installed. It should work with all of them, I think. Not 100% sure. At least the original 4K part of DesTest can run without those chips. Not sure if the full version of the test can work with those. That'd have to be a question for Matt Desmond, who will probably comment on this video to let us know. All right, there we go. It's looping again, completely fine. No errors in the RAM, which I'm not surprised. These NEC RAMs, by the way, they're slightly warm, not burning hot, just ever so slightly warm. And they are running properly. Notice the character ROM checksum changes every single time. It was something else a second ago. So that really just does confirm that this chip is totally dead. But we don't necessarily need confirmation, because literally just taking out the DesTest cartridge, that is our confirmation that that chip is bad. If this chip were removed from the board, it would look like that. So speaking of that, let me yank it out of the board. Ow, I just touched it again. I gotta stop doing that. That is crazy how hot it is. Okay, that came out a lot more easily. I think, well, because I applied heat as I was desoldering, and I applied heat removing the chip. I think that's kind of the trick. Just move that over there. Of course, there was that pin that I cut that I have to remove. The other one that I had cut before, that came off on the chip. It was that one there. That one actually stayed on. Unlike the RAM, that came right out. Why was there such a difference? I'm not sure. Like I said, I just applied heat to the bottom side as I desoldered versus not. I didn't do it on the RAM, and that was really hard to get out, but with heat desoldering, it just did a better job. And the chip just came right out so much more easily. For replacement character ROMs, there are loads of chips you can get that you can replace this ROM with. Many modern alternatives, I'll put a couple here, links in the description. But you can also use TMS 2532s. These are pin compatible on the 64 specifically, not always. You can't always reuse these, but they work in this machine. One problem with these particular EEPROMs, they can be hard to program. So 2532s can't be programmed in something like a Mini Pro or any of those TL866 kind of things. But I think I have a programmer I can program this with. I think it's this, the GQ 9x9 True USB Programmer. I think I also need to give it 9 volts DC. I think it uses both. So let me get that hooked up as well. Okay, here's the software, GQ 4x4 1.0. It's probably newer software. I haven't used this programmer in ages. But clicking supported list does bring this up, TMS 2532. Looks like read only for the A variant. Oh, this is an A variant. Versus the older one, 25 volts, that allows you to program it. Okay, that's annoying. So I can't use this to program this. There's another one further down, 21 volts, does work. I don't know what the programming voltage of this chip is. Hopefully it's 21 volts. Okay, cool. Okay, so we have this one. That's the A read-only one. Why? I don't know. Well, let's try the 21 volts. Okay, select. So it actually updates the firmware on the programmer. Every time you select a new device, it does show you how to insert the device, which I just inserted. So let's do device blank check. Or maybe get ID. Okay, no, it doesn't have an ID. Blank check. Chip is blank. Cool. Over on Zimmers, we can download the character generator. There's a bunch for other languages, but this is the one that we need, 901.225.01, which is exactly the chip that I took out from the machine. So here's that file, 64.bin that I just downloaded. I think we can look at buffer. Yeah, there it is. And let's try to write this. Hopefully it works. One thing I know is if I use the wrong profile without the A, 25 volt one, it kills this chip. I've done that before, unfortunately. It's not like there's a million of these chips floating around. There we go. I think that's a Commodore 64 character generator. And I just need to straighten the pins out since these sockets that I put in are kind of annoying. You got to make sure that your pins are kind of vertical up and down as much as possible. I mean, I don't know. This was obviously new old stock. I think I bought this from AliExpress years ago. It clearly looks brand new. Or if it was pulled out of something, they did a great job. So I'll just carefully get that in. There we go. All right, here we go. We'll know very quickly. Oh yes, it freaking works. There it is, looking perfect. The TMS 2532A is drop-in replacement with the character ROM, and I think the basic ROM. These two can be programmed with one of these EEPROMs, no problem. It just works. And we put a little label on there just for covering up the window more than anything, because people will complain if I don't do that. 901.225.01 replaced. One thing I have to warn you about is I ordered these chips, these EEPROMs 2532As, and they were fakes. Well, they were rebadges. They are actually Hitachi 2732s, which are completely not compatible. No, you cannot use them interchangeably. How did I figure that out? I think I looked with a magnifying glass or a microscope through the window, and I could see Hitachi logos. Yeah, there it is. TMS 2532. Absolutely not. This is really a Hitachi, or maybe it's a TI 2732, but I wrote Hitachi on here because I think when you look through the window with a microscope, you can see Hitachi logos. Either that or the words Hitachi. So yeah, the first batch I got were these fake ones, which is actually kind of wild because you really have to sand these down because this is a ceramic package and there's a window on there. So they did it, well, in a way that to try to kind of hide the shenanigans that they did. But as I said, I ordered another batch and that's where these ones are, and these obviously are the real thing. Since I have the diagnostic test harness, might as well use it. Looks like this came from Mike. Thank you very much, Mike, for sending this in at some point in the past. I know I haven't done much 64 repair stuff lately, but it is always nice to have these tools available for full and thorough testing. And with everything connected, the last thing to plug in is the loopback for the IEC port. So we're going to plug in the non-dead test, the regular diagnostic cartridge. And let's see if this finishes. But yeah, there's a lot of audio noise, or video noise, I mean, on the audio channel. Mark over at the Retro channel recently did a good video kind of exploring all the various possibilities of quieting that down by taking the audio input signal from the video jack and disconnecting that and doing some stuff. If you haven't seen Mark's channel and you like to repair 64s and work on 64s, I highly recommend you check it out. He's done some really, really cool experiments with the 64 and trying to figure out the noise issues. Looking good. Oh, okay. Well, I guess I had my speakers turned up quite loud, which maybe is why there was so much noise. Because all 64s are noisy, it's just how it is. Especially when, you know, they're in the original motherboard. Everything sounds perfect there. Absolutely perfect. That is cool. And obviously all the tests are passing. Let's just test this keyboard out. Oh, you know what? you can't really do that because without the springs, these plungers are held down. Well, let's just give it a test anyways. So this is a good little keyboard tester. This is on my Kung Fu Flash. Oh, see, those keys are held down right now. See if I shake it. So they're working. It's just the plungers are broken. So not every key is necessarily going to work with these held down. But actually, so far, everything is working. And I don't have to push hard or anything. This keyboard is in good shape. That dust cover did the trick. It's just too bad those plungers are bad. Yeah, fully functional. I'm not going to fix this keyboard in this video because there's a million videos on how to do that. Basically, you just take all the little screws out. Oh, there's some kind of mold back here. Take all the screws out. The PCB lifts away. Then you can pull the plungers out through the backside, push these through, put new plungers in, new springs, new keycaps, put the back PCB on, and clean it under there. But this keyboard's working perfectly, so I don't think it even needs that. And this will be a 100% fully functional keyboard. And obviously, good scrubbing of the whole top case will get rid of all that gunk that's in there. You know, a little WD-40 is a good solvent to get the sticky adhesive stuff off. And this could be made to look really good. Obviously, the discoloration is still going to be there, but I think just with some cleanup, it'll look a million times better than it does here. So what I'm going to do is I'm just going to use the keyboard from the ZIF64 just so I can test a little bit further on this machine just to make sure that the SID is really sounding as good as it possibly can. You know, we're all good. We already know that that keyboard input's working because the diagnostic harness or test harness we were using does test all that. So we can try playing a couple SID tunes. This does not have a built-in SID player, at least this version of Kung Fu Flash 1.5, the firmware that's on here. But we could just use a SID player. And then I can play some tunes. The video output's really good. There's no real jail bars or anything. It looks great. So we need to play 6581 SIDs. I mean, we could play the other ones. They just won't always sound perfect. Let's just try one of these. Yeah, everything is working really well. This SID, those 6581 R4ARs, awesome SIDs. They are very awesome. Okay, so I think you know what that means. Even though this is not the easy Flash, I can still run the same programs from the Kung Fu Flash. ADB NTSC is Adrian's Digital Basement 8-Bit Dance Party, the NTSC version. Pretty sure it is. Let's run this. Oh yeah, and I can push the space bar to get the little sprite bobs on there. 8-Bit Dance Party. It's been a while, hasn't it been? Oh yeah, sounds good. Let me turn the music up a little bit. Perfect, absolutely perfect. Okay, that is gonna be it for this repair video. This machine freaking works. The next owner of this machine will just have to do some work scrubbing the computer, cleaning it as much as possible, and I will give them the replacement keys, springs, and plungers so that this will be a fully functional, original 1986 Commodore 64. Considering now you're watching this video in 2026, that means this computer is 40 years old and still working, other than, of course, this character generator that went bad and a couple NEC RAM chips. I hope you found this repair interesting, especially if you still have broken 64s. Really, I just wanted to show that you just need something inexpensive like this to troubleshoot and get these things working. And a huge thanks to Joe over at the VintageTek Museum for creating this CurveBug and giving me one so I could test this out. I know in this situation, the CurveBug wasn't a slam dunk when it comes to figuring out exactly what was wrong with the machine. I was able to kind of do that with this cheap oscilloscope / multimeter. But I think with the right situation where you have some subtle faults, this thing could be really, really invaluable. And the fact is, with the chips out of the board, like these RAM chips, we could definitely see that these RAM chips were looking weird. And if you have a bunch of them and you want to see if one's bad out of the board, I think that this could really be helpful for that kind of thing as well. And I'm not sure just checking with the multimeter in resistance mode necessarily would show you a fault. Although ultimately what the CurveBug is doing is sending out ramps of voltage, probably from 0 volts to whatever, a couple hundred millivolts. And then we're seeing the visual representation of the current draw or something like that on those on-screen displays, which is why it's kind of useful versus something like just a single point in time using the resistance mode. Anyway, I'll put links down below in the description for this. If you're interested in picking one of these up, all the proceeds for this go to the VintageTek Museum to help keep that place open and operating. It's a fantastic museum. If you haven't been already, highly recommend you check it out. Of course, I'll have a link in the description for that as well. And yeah, first video of 2026, fixing a 64. It kind of felt like riding a bike a little bit. I thought I was maybe going to get stuck with this one, but no, there was no getting stuck. It felt good again to be working on these things. And Paul, who worked on this last, he got stuck trying to fix this thing, and DesTest, I didn't even test DesTest beforehand because there wasn't really a point. Burning hot chips equals system that's completely broken. And he told me that when he did run DesTest, that was the label that was on here, it didn't really provide anything useful. But how could it? DesTest can't really work when the RAM is completely destroyed. And of course, data line 0 was also crashed, so code can't really run from the cartridge or the ROMs when the data bus is so trashed. So I'm amazed it even did anything. Like, it created a purple border like he said it would, because frankly, that means some code was running somehow, which is kind of shocking considering the entire data bus was trashed on this machine. So if you enjoyed this first video of 2026, I appreciate a thumbs up. We'll be getting back to the Apple Lisa very soon. I want to get that machine finished, put back together, and running LOS so I can really play around with that machine, and then maybe explore some of the other operating systems that are available for it, and just, yeah, kind of see what the Lisa is all about. And that's going to be that. Huge thanks to my supporters. Huge thank you to you for being a loyal viewer of my channel for so long. It's been amazing being able to do this stuff, which was my hobby, and now I think I've been doing this full-time for a couple of years now. I forgot, to be honest, was it 2.5 years? And it's been amazing. I do not regret for one decision making the switch to doing this full-time. I absolutely, absolutely love it. If you enjoyed this video, thumbs up, comment down below, and all the usual rest of the YouTube stuff, and that's gonna be that. So stay healthy, stay safe, and I'll see you next time. Bye.